hello, friends, family, and random internet strangers, and welcome to week 3 of Let's Read Code. Turns out when I was going through my notes and splitting up the chapters and reading assignments and stuff, I kind of goofed and really should have had you. A video started playing on top of me. Um, Anyway, really should have had you read chapter 8 this week and maybe had you do chapter 6 last week, but that's okay. So I'm going to end up going over chapter 8 this week too. So it's okay. It's very detailed explanation of something that's not necessarily all that complicated. So we'll be fine. So let's talk about telegraphs. So first bit of chapter 6 talks a little bit more about Samuel Morse and the history of the telegraph. So Samuel Morse, dude who made the telegraph, also was a painter and photographer and failed politician. Um, Very interesting history of all of the things that he was involved in. But so he's the one who kind of came up with the whole telegraph Morse code system, along with a couple of other people that helped that history has kind of more or less forgotten about, as tends to happen with these things. So a couple of the other big players, a guy named Alfred Vail, the first large scale, like actual big long distance telegraph transmission, he was the guy on the other end. He also provided a connection to a big like metalworking foundry company that helped produce a lot of the early telegraph equipment. Then a chemistry professor named Leonard Gale, who worked a lot with Morse to figure out, okay, if we're going to send this electrical signal over 300 miles, how do we actually build the wire, design the circuitry to make that work? So, lots of historical bits there. Get into talking about electromagnets, which are kind of important because without this, which I actually have a thing kind of sort of built over here and some stuff to show how this worked in the telegraph system, not only the first easy bit of either activating a pin to tap out the dots and dashes on a piece of paper or just make sounds. That's how it ended up working more effectively because having to read the paper and transcribe it back into hitting a button too much work for people apparently. Um, so I actually have built over here a. So here's my first electromagnet that I tried. Just a bolt with some very skinny wire wrapped around it over and over and over and over again. Turns out that didn't quite have enough oomph to actually move anything. So ended up with version 2. Camera a little bit is actually a socket wrench with a bunch of tiny wire wrapped around it a lot. And that's hooked up to a basically a cell phone charger for the power because 9-volt batteries weren't quite cutting it either. But I've got it hooked up to this button over here, and hopefully you should be able to see it move. And hopefully you can hear it too. So as I'm pushing this button, it's actually turning on the electromagnet and moving the little piece of metal that I have taped to the table. So that's basically how the early telegraphs worked, just at a much larger scale. The 5-volt, 2-amp power supply I hooked up to this thing might get across my house, maybe. To get like the 300-mile maximum run that Morse ended up getting to, you need like 300 volts and a couple hundred amps to actually get a signal that's strong enough to make it that distance. So the next thing I kind of talked about was, okay, we had this electromagnet that's connected to a bar that's making a clicking sound. What if we connected that bar that's making the clicky sound to another button so that we could send the signal uh, further than the maximum distance that we can run one big wire? So we have invented the relay, basically, which I have here, disconnect a couple things. So this is a relay. Just bought this one from, I don't know, some electronics retailer at some point to use for experiments and demonstrations and stuff. So this works very similarly. I'm going to hook up power again. And I don't know if you can actually hear that, but as I'm hitting the button, there's a little electromagnet in there that's making a little piece of metal move back and forth. So I have set up over here a little step. So this is basically controlling one electrical circuit with another electrical circuit. So I hooked up my button and my cell phone power charger doohickey to the what we call the control side of the relay here. And then over here, I have the power from microcontroller going in and back out and through this LED and back to the ground side of the Arduino. So when I hit the button on the relay, it turns the LED on. Because when I hit the button, it turns on the little electromagnet inside here, which causes the little piece of metal that's in here to swing from like being angled up here somewhere to connecting from this side to this pin over here and completing the circuit and making the LED light up. That makes sense? Anybody horribly lost and confused so far? No? Great. So, that's relays. If we had enough of those doohickeys, we could actually start building a computer right now. But it would be painful and very large and take up a lot of electricity. So we'll learn later how we can do that a little bit more efficiently. So the next chapter So the next chapter and the chapter after that I kind of skipped over the divider between, it's talking about counting. So if you'll remember from okay, so if you remember from, I don't know, second, third grade maybe, they're teaching you about numbers. So we have like number 125, right? So that means you have so it means you have 5 ones, 2 10s, and 100, right? Everybody remember this? Yes, good. So chapter 7 kind of goes over sort of the evolution of how people wrote down numbers. So going from simple tally marks to more like Roman numerals and into Arabic numerals like we use today to do numbers like that. Chapter 8 takes this a little bit further and points out that these numbers here are the place values here are powers of 10, right? So the next one out is 1,000. Keeps going on and on like that. So what if we didn't use 10 for our base? What if we used, for example, 8? He uses that as an example where it talks about like the reason that we use base 10 for everything like that is because, you know, we have 10 fingers, so it makes it easier to count. Kind of walks through the example of, okay, how do cartoon characters that only have 8 fingers count? So look at that. So this becomes 1, 4, 5, 12, isn't it? It helps if I can do math. All right. So now let's say I write a number like so it looks like 117, but since we're working in base 8, 117 doesn't necessarily mean 117 like we think of it. So we want to figure out what that actually means. That means we have 7 ones, 1 8, 1 64. So if we add those together, we get so nine in regular people counting. Does that concept make sense? Yes? Great. I'm seeing nods. That works. So we can do that whole similar setup with any number we want. So there are 2 very common ones that we'll see in computery situations. 2 is kind of the most common one. Right? This. Right? So the other thing about this is the base number you have here controls how many digits you have to work with. So when we're working in base 10, we have 10 digits, 0 through 9. When we're working in base 8, we have 8 digits, 0 through 7. When we're working in base 2, we have 2 digits, usually 0 and 1. Mix things here. So we have a number like 1, and we want to convert that into decimal or regular people counting, base 10. We've got 1, 1, no 2s, 1, 4, 1, 8. All right, 13 in base 10 is equal to base 2. So do a little interactive exercise here. If I were to write 1, 1, 1 in binary, what is that in base 10? Anybody?
maybe?
You are correct. The answer is 15 because we have an 8 and a 4 and a 2 and a 1, which when added together gives you 15. Or try this. How about 1? I just made up numbers, so somebody throw out an answer and we'll see if you're right.
138.
138, he says. Let's find out. So if I go put these in, that's 4. So we have 4.
Whoops.
8 plus 2 is not quite. I think you had. I think you went one further here because the next one would be 128. So skip a step somewhere. Okay. Let's see if you can now go the other way. What is 60 in base 10? What is that in binary?
Would it be 6001?
It can't be 6.
First. Oh.
All right, so the easy way to do this, what is the largest power of 2 that's less than the number that we want? This case is 32. Okay. So, what's 60 minus 32?
8.
8. Can we take 16
Wait,
away?
no.
Take 16 away from 28? We sure can. What does that leave us with? 12. Take 8 away from 28. Sure can. That leaves us with 4. Hey, look, 4. What's that leave us with? 0. So the answer is 111100. So if we try that again, it's 96.
One one zero 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 zero.
1 1 0. I think you missed a 0, but yes. Okay. So that's how binary works. I'm going to take a slight detour elsewhere to the other commonly used counting system, is base 16, also known as hexadecimal. So if you've been paying attention, if we have base 16, if this number is 16, that means we need to have 16 different digits to use, but normal counting only has 10. So what do we use to keep going? We usually end up using letters. So $49. Yeah, you don't think about, because of how we use hexadecimal for things, you usually don't need more than 2 digits. So, for example, let's say we had the number AA. So that means we have, since we're counting now, we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So this effectively means we have 11 ones and 11 16s. Is 76. 187 is our final. So AA in base 16 equals 187 base 10. So the reason we see that a lot, if you remember back about 2 weeks, actually no, that was the first week. So yeah, 2 weeks ago, when we were talking about data storage. So we're talking about, we have 1, a bit is a 1 or 0. Byte equals 8 bits. It also means 2 bytes is 16 bits. So once upon a time, back in the olden days of computing, people used to use octal a lot more, base 8, because um, 2 digits could get you every possible value of a byte. As storage capacities kept getting bigger and bigger and bigger, 1 byte values became less and less useful. So 2 bytes or additional bytes uh, kept getting bigger, or we started using more storage space, which means the numbers that we used to write down the values that we were storing kept getting bigger and bigger and bigger, which means the numbers that we were writing down in octal kept getting longer and longer and longer and longer. So if we write it in base 16 instead of base 8, it makes our numbers a heck of a lot shorter. So anyway, so now that we know how to count in binary, the next step eventually will be to take some of the electronics knowledge that we've gained and how everything works on things being on or off, and the fact that we now know how to count in binary and kind of do math in binary, and put those two things together and get circuits to start doing math for us. So that's kind of what's coming next. I think that is everything covered for today. Anybody have questions, comments? No?
Sure.
Okay, what is your question or comment?
Will next week have more math because that might not be good.
uh, kind of, but it's all brand new math that you've never seen before. So it kind of doesn't matter. So it'll be less about, it is math, but it's also like logic. So it's a way of thinking about things that are happening and representing that with numbers and then doing things with, which will eventually let us do actual math.
Okay.
Anything else? Other comments, concerns? No? Okay. So next week, yeah. So next week, talk a little bit about more coding, like as in ways of representing information just with binary, and then start getting into sort of doing math with bits and circuits and stuff. So next week I'll also probably show you how to do this with a little simulator program I found on the internet, as well as how to do it in Minecraft, which is infinitely more fun. So, if nobody has any questions, I believe that is it for this week. Thanks for coming. See you next Saturday. I always forget to pull up the stop stream button. Oops.